Okay, let's discuss this question. This DMB3301 thermo fluids question from mechanical engineering department. The question, I'm going to read this question. A gas, a gas has a density of 2 kilogram meter minus 3 at a pressure of 1 bar and with a temperature of 15 degrees Celsius. A mass of 0.9 kilogram of the gas requires a heat transfer of 175 kilojoule to raise its temperature from 15 degrees Celsius to 250 degrees Celsius while the pressure of the gas remains constant. The above first question is the characteristic gas constant of the gas. Let's read the question again. A gas has a density of 2 kilogram uh, meter minus 3 at a pressure of 1 bar and with a temperature of 15 degrees Celsius. A mass of 0.9 kilogram of the gas requires a heat transfer of 175 kilojoule to raise its temperature from 15 degrees Celsius to 250 degrees Celsius while the pressure of the gas remains constant. Pressure of the gas remains constant. Let's move to the question. Okay. Uh, uh, if you want, you can take a screenshot of this question. We can move to the answer. First, we have to find the characteristic gas constant. Uh, Now, the given data is the gas density of the gas. Let's assume that uh, this is gas. The density of the gas rho. The density of the gas rho is equal to 2 kilogram meter minus 3. 2 kilogram meter minus 3. This is the density of the gas. Uh, will, the pressure is 1 into 10 to the power 5. The pressure P is equal to 1 bar. 1 bar is equal to 1 bar is equal to 1 into 10 to the power 5 Newton meter minus 2. Newton meter minus 2. Or we can use Pascal, the unit Pascal instead of Newton meter minus 2. Okay, this is rho, this is capital P, pressure. Uh, in which temperature we calculate the pressure and density? We calculate it in T is, theta, sorry, theta is equal to theta is equal to 15 degrees Celsius. 15 degrees Celsius. We already know we can do calculations in degree Celsius. You must convert the degree Celsius to Kelvin. Now we are going to convert to degree Celsius Kelvin. The equation is T is equal to T is equal to theta plus T is equal to theta plus 273.15. Okay. T is equal to theta plus 273.15 Kelvin. T is equal to theta plus 273.15 Kelvin. This is the equation. This is the equation to determine the to convert degree Celsius to Kelvin. Therefore, T is equal to theta is 50 degrees Celsius. 15 plus 273. 273.15 Kelvin. If we sum the equation, we will get the final result that T is equal to uh, 288 288.15 288.15 Kelvin. This is the equation of This is the initial temperature. Temperature of this is the initial temperature of the gas. Okay. Now let's read the question. A mass of 0.9 kilogram of the gas requires a heat transfer from 15 degrees Celsius to 250 degrees Celsius, while the pressure of the gas remains constant. I think I missed this is the question. I missed one. A mass of 0.9 kilogram of the gas requires a heat transfer of 175 kilojoule to raise its temperature from 15 degrees Celsius to 250 Celsius. We want the 175 kilojoule. We want. Therefore, this is the real question. Uh, Initially, this is the volume. We Let's assume that the gas, the gas, the gas is initially the gas is in this container. The volume of the container, let's assume that V1. Okay. Now, if we increase the, if you read the question, it mentioned that the pressure of the gas is remains constant. Therefore, uh, your, according to the question, the temperature is moving to 15 degrees Celsius. 15 degrees Celsius to uh, 250 degrees Celsius. 250 degrees Celsius. Celsius. But the pressure is constant. If the initial pressure is P days, now also P days. Therefore, we increase the temperature 15 degrees Celsius to 250 degrees Celsius. But if the pressure is now also constant, we can assume that that the the volume of the container will be increased. Therefore, initially V1, V2, it will be increased. Okay. How much energy do we want to increase the temperature from 15 to 250? That's the 175 kilojoule. 175 kilojoule. 175 kilojoule. Now the first question is the characteristic gas constant of the gas. Okay, let's see the okay. The characteristic gas constant of the gas. We already know the equation of the ideal gas. We already studied in A-level chemistry. The the equation of the ideal gas is PV is equal to nRT. PV is equal to nRT. P is equal to nRT. We already know this equation, but this equation is only for ideal gas. This R is really uh, universal gas constant. This is the universal. This R is universal gas constant. But we have to find the characteristic gas constant. Therefore, we have to convert the equation to uh, we have to convert this equation to find the characteristic gas constant. Let's assume that the characteristic gas constant is Rc. Okay. Now let's move. Now PV is equal to nRT. PV is equal to nRT. PV is equal to V is equal to mole. P is pressure, V is volume of the gas. N is we can say that volume V is volume of the gas or volume of the container. N is mole of the gas, R is gas constant, uh, universal gas constant. Uh, for ideal gas, we already know R is equal to universal gas constant of the gas. Ideal gas will be R is equal to 1.834. Oh, let's check again. We don't need this that number. They are the For ideal gas, the universal gas constant R will be R is equal to 8.1314 joule mole minus 1 joule mole minus 1 Kelvin minus 1. R is equal to 8.314 joule minus 1 Kelvin minus 1 is the universal gas constant of the ideal gas, but we have to find the uh, characteristic gas constant of the gas. Therefore, PV is equal to nRT. PV is equal to nRT. This is the equation of ideal gas. Now we are converting. PV is equal to N is equal to, we already know, W by small w by capital M. This is the mass of the gas. This is the molecular mass of the gas. W into, we already know, mole is equal to mass divided by molecular mass of the gas into R, universal constant of the gas, into T, temperature in Kelvin. Now, now, now let's T is equal to, I move this B to move B under the W, like W by V. W by V, W by V into R by M. R by M into T, the temperature in Kelvin. Uh, T is equal to W by V into R by M into T. T. Now we already know this. This is what is this? P W by V. This is mass. This volume. Mass divided by volume is density. This is the density. Therefore, P is equal to rho. We substitute rho instead of W by V. The density of the gas. Therefore, this is the rho density into, this is the characteristic characteristic gas constant of the gas. We have to find for this question. Therefore, R by M, this is the characteristic. Therefore, let's assume that this is the RC. This is the characteristic gas constant RC. That is, this R is universal gas constant of ideal gas. This is the uh, characteristic gas constant RC into T. This is the temperature in Kelvin. Now we have to, the question is we have to find the RC. Therefore, we we make some arrangement in the equation. RC is equal to RC is equal to P by rho T. R is equal to P by rho T by T by rho density of the gas into temperature in Kelvin. Now we already know they have given the data, the temperature. We only know the density for initial stage. We don't know the density for last stage. They gave the density for at the initial stage. You can find in question that initial density is 2 kilogram per kilogram meter minus 3. Pressure 1 bar, which is 1 into 10 to the power 5 Pascal. In initial temperature is 15 degrees Celsius, which is equal to 288.15 Kelvin. Therefore, P is equal to 1 into 10 to the power 5 Newton meter minus 2. 1 into 10 to the power 5 Newton meter minus 2 or Pascal divided by 2 kilogram meter minus 3 2 kilogram meter minus 3 kilogram meter minus 3 into T initial temperature, which is equal to 288.15. 288.15 of Kelvin. If you calculate this equation, finally you will get the final result that the results will be 173 173.521 173.521 joule kilogram minus 1 joule kilogram minus 1 Kelvin minus 1. This is the final answer we have to find. This is the R. This is the R, which is which R is characteristic gas constant. This is the final answer. 173.521 joule kilogram minus 1 Kelvin minus 1. Now let's move. How did you how we if you find the equation is 2, please wait, Newton meter minus 2 divided by kilogram meter minus 3 into Kelvin. We find in denominator you will find Newton meter minus 2, here kilogram meter minus 3 Kelvin. But here you will find different unit. How did we get this unit? Let's 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 discuss about that conversion now. Okay, we we write the unit again. Newton meter minus 2. Newton meter minus 2 divided by kilogram meter minus 3 kilogram meter minus 3 kilogram meter minus 3 into Kelvin. Now this meter minus 3 in numerator meter minus 2. If we multiply by meter cube in denominator and the numerator, the meter minus 3 and meter cube will be cancelled, which is equal to m to the power 0, which is equal to 1. Therefore, it will be cancelled. In numerator, we will find the final result m cube into m minus 2, m 3 plus minus 2, m3 plus minus 2 to m to the power 1 equal to m. Therefore, in numerator Newton meter, in denominator kilogram Kelvin, kilogram Kelvin. We already know which is the equation of Newton meter is joule. We already know work is equal to force into distance. We already know this equation. Work work done work done is equal to applied the force applied force into distance. How much distance we move? We applied force. How much distance we move the thing? by the force. Therefore, F is Newton. This D meter, Newton meter. Therefore, the other equation of the work done is joule. You already know this is a simple one. The joule divided by kilogram Kelvin. This is the joule kilogram minus one Kelvin minus one. We found in the final answer. Okay, let's discuss the second question. Big question. We have now find the discuss about A question. We now find in next video we can find the big question. Okay, bye.